So let's take a look at motional EMFs. So we're interested in the generation of EMFs by the motion, and I want to stress motion because later on we're going to be talking about effects where we have no relative motion of fields and conductors. We'll also be talking about Lenz's law. If you remember back to the Lorentz force, if we were to divide by the charge, we'd have the force per unit charge. So here I have the F over Q, and this is the generalized version of the force acting on the charge. The magnetic part is V cross B, and so if I separate that out, the force per unit charge in the magnetic field is equal to V cross B. Well, this term can result in EMFs. These would be generated by, say, the motion of wires, which contain charges, in the magnetic field. Consider the loop that I show here, where I have B into the page, like this, and V is to the right. So notice that we have a portion of the loop in the magnetic field and a portion outside. Now realize that any charge in the wires and, of course, in the resistor that are outside of the B field, those will not experience any force. So there's no force outside. So it's only in the area here where this part of the loop is inside the B field that we would have a force due to the motion of the loop. Every plus charge, every plus free carrier, where it's in a region where B is not equal to 0, will experience this V cross B force. And we're going to call that, again, our F plus. We've already eliminated the region out here. For these segments, B to C and A to D, the force per unit charge is in the upward direction. So to see that, you have V in this direction, you have B into the paper, so if you do V cross B, you get a force in the upward direction. In terms of the wire BC or the wire AD, you'll notice that the force is perpendicular to the wire. What that would do is we shove positive charge on this side of the wire and minus charge on this side of the wire. It separates the charge, but it does not contribute to the potential push of charge around the circuit. So we can ignore these parts of the circuit. However, the segment AB, which has positive charges, all of those would also experience the F plus. It's along the wire, so it induces a current. And so we would have positive charges moving up, and if we had negative charges, of course, they'd go in the opposite direction. This part of the circuit is acting like a battery in the sense that it's shoving charge in the right direction, inducing a current, and because of the conservation of charge, that current will have to flow through this entire loop like this. If we look at the force, we've already said what it is. It's V cross B, but let's put in the directions just to make sure we're right. We bring out the magnitudes of V and B, and so we're left with a cross product of unit vectors. X is the direction of the velocity vector, minus Z is the direction of the B field. So if you take this cross product, you end up with the unit vector Y hat, and of course times VB. Well, Y hat is in the upward direction, so we indeed have them along this arrow here. If we take this force per unit charge, we have to remember that this is equivalent to an E field, because the electrostatic force divided by charge is capital E, the vector E. So we can equate those two vectors. So E and V mag are very, very similar. If we integrate the E field around a loop, this will give us this integral here. That's equal to the integral of F plus mag. That's equal to what we call EMF, because it's the electromotive force, it is the electric field which is driving charge around the entire loop. This E field is only non-zero, or the F mag is only non-zero, between the points A and B, because of the fact that the F is along the direction of the flow of current. So what that means is that we only have to integrate this function from A to B. Coming back to our expression for V mag plus, putting it into the equation, we have a Y hat for the unit vector and the magnitude VB, and for dl, in this case dl is along the y direction between A and B, and so we get y dot y hat, which is of course 1. So we're left with B times B times the integral of dl from A to B. And that's given by this quantity h. If you come up here, h is the width of the coil, and so that would be entered in that point. Now putting in v as dx dt, we can see that we have x times h, which is the area of the curve that's inside of the magnetic field. So the change in the area that's inside the magnetic field with respect to time times b will give us our EMF. If you look at the concept of flux, the magnetic flux through that area, phi sub A, is equal to B times A. This area, which is the portion that's inside the magnetic field, the rate at which that area is changing, that will give us then the rate that will produce the EMF. So here's the flux, BA, and so if we take EMF being equal to B times dA over dt, we can see what we're doing here is we're changing the flux. So d phi dt is equal to the EMF, and this is in magnitude. Remember that what we've done was derived from the Lenz force, and so we're talking about things that are generated by the motion of the charge through a magnetic field. Normally what we do is we add a minus sign to remind us how we determine the polarity of this EMF. For this case that we've just done, the direction dictated by the Lenz force is actually correct, and so the current flows clockwise in the view shown. That's convenient, but more frequently what we do is we use Lenz's law. So let me just go back and note one again. This arrow here is showing the direction of the current. The current is flowing this way, which means that it's flowing this way through the resistor, so we would call this end plus and this end minus in order to get current to go through the resistor this way, and so the EMF across here would have plus on this end, minus on this end. Okay, so let's look at Lenz's law. Well, an analog of Lenz's law is called the lazy student's law. If a student is stretched out on the couch, half or fully asleep, the student is opposed to getting up. He or she will resist such a change. And so here we have the couch potato. There's actually another one over here. There's a resistance for this couch potato to get up. Lenz's law has to do with the polarity of the induced EMF and the direction of the induced current. So what Lenz's law says is that these quantities in a loop will oppose the change that created it. And so the induced magnetic field inside any loop of wire always acts to keep the magnetic flux in the loop constant. So that's why we put this minus sign in here reminding us to apply this law. Let's consider the case where we have a bar magnet which is being pushed in towards the coil with some velocity v, and we want to determine the direction of the induced current and the polarity across some load resistor here. So realize then if we're pushing a north pole towards the coil, then B will be in this direction, and because we're approaching the coil, the change in B is in this direction here. However, if we look at the induced B, it has to oppose this change here. It's trying to keep the field inside a constant, or at least as much as it can. To do that, if B is in this direction, B induced, then use your right hand rule, so wrap your fingers around, and you can see that the I induced required to give us that B direction is shown here. For the front of the coil, it's heading in this direction. Carefully look at the currents. If current is going this way on this wire here, and then the return wire it's going this way, then look at the current inside the resistor. It's going along this direction here. What that allows you to do then is to say that if current is flowing in this direction, this end of the resistor is plus and this end is minus. What we've got here then is both the direction of the I induced and the polarity of the EMF. So that's again why we put the minus sign there. Consider the force on the magnet moving to the left, and consider I induced and B induced. And so what that looks like is a pair of magnets shown here. the coil is acting like a bar magnet that repels this magnet here. As you push this magnet towards the coil, you have to push in order to keep it moving. So what that means is you're doing work. Pushing the magnet to the left requires work, which is equal to F times X. The work per unit time then is going to go into the heating of the resistor. This is power, of course, but what it's saying is that if you're pushing this towards the coil will respond in such a way that you have to push against the field generated by the coil. And that's why we put this as a north-south bar magnet, which is pushing on this magnet here. If you violate this, so in other words, you reverse the direction of I induced and the direction of B induced, then what would happen? Well, first of all, I've shown the flip. So here we have the B induced in the same direction as delta V. We flipped I induced. So I induced in the resistor is flowing this way, and it reversed the polarity of epsilon. Well, what does that look like? Well, take the direction of B induced and look at what that would look like in terms of bar magnets. It would look like a bar magnet that's oriented this way. A south end here and a north end here. You've got a north and a south, so therefore it would attract. You would still get the heating, so you've generated the heat. You have something that is being pushed or pulled into the coil, and so you've gotten heat energy without doing any work. You have just made a perpetual motion machine, patent it, and you become very rich. Well, you can't do that probably because conservation of energy says forget it. In terms of conservation of energy, this is not allowed. So therefore we have to go back to Lenz's law, which really is a statement of the conservation of energy, and we see that we have to flip back to the original values.